Today, we're tackling something huge, really one of the grandest ambitions in physics, trying to understand the fundamental nature of reality itself.
And we're doing that by plunging into the standard model of particle physics. It's often called the theory of almost everything, which gives you an idea of its scope.
Exactly. So our mission today is to unpack what the Standard Model actually is, how it came about, what it describes.
Its building blocks, the fundamental particles and forces.
Right, and also, crucially, where it falls short. Because it does leave some of the biggest mysteries totally unsolved.
Absolutely. And for this deep dive, we're drawing our information from the well-regarded Wikipedia article on the standard model.
Yeah, think of this as your shortcut to getting really well informed on this. We're hoping for some surprising facts, maybe a few aha moments about that tiny, tiny subatomic world.
So shall we start with the big picture? What is the standard model?
Okay, yeah. At its core, what are we talking about here?
Fundamentally, the standard model, or SM for short, it's our best theory right now for three of the four fundamental forces we know about.
Okay, so which ones are those?
That's the electromagnetic force, the weak nuclear force, and the strong nuclear force. It also classifies all the elementary particles we currently know exist.
The basic building blocks. And this is like the first big asterisk, isn't it? It leaves one major force out.
It absolutely does, a huge one, gravity. The standard model explicitly excludes gravity.
That feels like a pretty big omission for a theory of almost everything.
It is, and it's arguably the biggest challenge in fundamental physics today, reconciling gravity with this picture.
And this model, it wasn't just like dreamt up overnight, right?
Not at all. It was developed piece by piece, really throughout the latter half of the 20th century, and kind of solidified into its current form around the mid-1970s.
And its track record since then has been, well, pretty amazing.
Oh, astonishingly successful. It didn't just explain things we already knew. It made incredibly precise predictions about things we hadn't seen yet.
Like what sort of things?
Well, it predicted the properties of weak neutral currents and the existence and masses of the W and Z bosons, the carriers of the weak force. And these were later confirmed experimentally.
That's really the gold standard in physics, isn't it? Predicting something new that's then found.
Exactly. And the confirmations kept coming. You had the top quark discovered in 1995, the tau neutrino in 2000.
And the big one everyone heard about, the Higgs boson in 2012, that felt like the capstone.
It really was. Finding the Higgs was a massive experimental effort and a huge validation for the entire standard model framework. Each of those discoveries just added more weight to it.
So beyond just listing particles and forces, why is it such a cornerstone for, say, theoretical physicists? What makes it a paradigm?
Well, for physicists, it's this beautiful mathematical structure called a quantum field theory, QFT.
Okay, quantum field theory. What does that mean in simple terms?
Instead of thinking of particles as tiny points, think of them as, like, ripples or excitations in underlying fields that fill all of space and time. There's an electron field, a quark field, a photon field.
So everything is fields.
In this picture, yes. And the standard model uses this framework brilliantly. It shows how phenomena like spontaneous symmetry breaking work.
Symmetry breaking. Sounds complicated.
It can be, but the core idea is like this. Imagine the early universe was perfectly symmetrical, maybe like a pencil balanced on its tip, very unstable.
Okay.
Then something happens, the Higgs field acquires a value, and the pencil falls over. It picks a direction, breaking that perfect symmetry.
And that, falling over, does something.
It does. That symmetry breaking is precisely how particles like the W and Z bosons and also electrons and quarks get their mass. It's not random. It's inherent in how the fields settle.
Wow, okay. So the math explains why things have mass.
Exactly. And this whole structure, this QFT framework, it's the foundation. It's the basis for building even more speculative models, trying to explain things the standard model doesn't cover.
Like what?
Things like dark matter, or why neutrinos seem to have mass, which the original SM didn't predict. People propose new particles, like in supersymmetry, trying to fit those odd experimental results.
Right, trying to build beyond the standard model. That makes sense. Okay, this sets the stage really well. Now, how about we rewind? Let's trace the history. This didn't come from nowhere.
Absolutely. It's a fantastic story, really, of decades of work, brilliant ideas, crucial experiments. It really highlights how science progresses.
Where does the story even begin?
You could argue it starts way back in 1928. Paul Dirac writes down his famous equation describing the electron.
The Dirac equation, right?
And almost as a mathematical side effect, it predicted the existence of antimatter the positron, an anti-electron,
Right.
Sounded completely wild at the time.
Antimatter in 1928. Okay, fast forward a bit.
Things really pick up steam in the 50s. In 1954, Yang and Mills generalized something called gauge theory. It provided the mathematical tools needed later for the strong and weak forces.
Okay, mathematical groundwork.
Then a crucial experiment in 1957 by Chen Xingwu. She showed that parity, like mirror symmetry, is not conserved in weak interactions. Nature, at that level, can tell left from right. A huge shock.
That sounds fundamental, like finding a flaw in a basic symmetry.
It was, and it opened the door. In 1961, Sheldon Glashow took a big step trying to unify electromagnetism and the weak force.
Electroweak theory begins.
The beginnings, yes.
Yep.
Then 1964 was a massive year. Marie Gell-Mann and independently George Zweig proposed that particles like protons and neutrons weren't fundamental.
They were made of something smaller.
Exactly. They proposed quarks. Up, down, strange quarks initially. And in the same year, Oscar Greenberg introduced the idea of color charge for quarks, though it wasn't fully developed yet. That's key for the strong force.
Quarks and color charge, got it. What about the 60s continuing?
1967 is pivotal. Stephen Weinberg and, working separately, Abdus Salam took Glashow's electroweak idea and incorporated the Higgs mechanism.
Ah, the mass-giving mechanism we talked about.
Precisely. This is what gave the electroweak theory its modern form, explaining how the force carriers, W and Z bosons, could be massive, while the photon remained massless.
So the theory was looking pretty complete for the electroweak part.
Getting there, and theory kept leading experiment. 1970, Glashow, Iliopoulos, and Mayani the Jim mechanism. It solved some theoretical puzzles, but also predicted a fourth quark.
The charm quark.
The charm quark, yes. Then in 73, another breakthrough, this time for the strong force. Gross, Wilczek, and Pulitzer independently discovered asymptotic freedom.
Asymptotic freedom. What's that again?
It explains this weird behavior of quarks. They're bound together incredibly tightly, but if you probe them at very high energies, very close distances, they act almost like free particles.
That sounds backward. Usually forces get stronger up close.
Right. But the strong force gets weaker up close. This discovery really cemented quantum chromodynamics, QCD, the theory of the strong force, as the right description.
And were experiments catching up to all this theory?
Oh, yes. Also in 1973, a huge discovery at CERN. Neutral weak currents, interactions mediated by the Z boson. This was like the smoking gun for the electroweak theory.
And that led to Nobel Prizes.
It did. Glashow, Salam, and Weinberg shared the Nobel in 1979 for unifying the weak and electromagnetic interactions.
Meanwhile, were new particles still being found?
Absolutely. The particle zoo was expanding. Martin Pearl discovered the tau lepton in 76, a heavier cousin of the electron.
Another generation of matter.
And then Leon Lederman's team at Fermilab found the bottom quark in 1977. Then in 1983, the actual W and Z bosons were directly detected at CERN, with masses just as predicted by the electroweak theory. Huge confirmation.
So by the mid-70s, early 80s, the pieces were really falling into place. QCD for the strong force, electroweak theory.
Exactly. Experiments confirmed hadrons were made of fractionally charged quarks, solidifying QCD. And around 75, the name Standard Model started being used. Pies and Treman used it, though Weinberg might have used it earlier.
It really shows how science builds, doesn't it? Decades of work, theory, experiment, people all over the world.
It's a perfect example of that collaborative, incremental process. No single genius, but a whole community pushing the boundaries.
Okay, so that's the history. Now let's really dig into the components. The cast of characters inside the Standard Model. You mentioned fermions and bosons.
Right. At the most basic level, particles are classified by their quantum spin. Fermions have half-integer spin, like 12, 32, and bosons have integer spin, 0, 1, 2.
And that spin difference matters.
Hugely. Fermions obey the Pauli exclusion principle. You can't put two identical fermions in the exact same quantum state. Think of electrons in an atom. They have to occupy different shells or have different spins. This is why matter takes up space.
Ah, okay, so fermions are the matter particles.
Primarily, yes. Bosons, on the other hand, don't obey Pauli exclusion. You can pile loads of identical bosons into the same state. They're often the force carrier particles.
Got it. So let's start with the fermions, the matter, 12 of them.
12 elementary fermions, plus their corresponding antiparticles. We group them based on how they interact. First up, the quarks.
We met them briefly in the history bit. 6 types.
6 flavors, yes. Up, down, charm, strange, top, and bottom. Their defining feature is that they carry color charge.
Not actual color, right? Just a name for the charge.
Exactly. Just a name for the type of charge that the strong force interacts with. Because they have color charge, quarks feel the strong interaction.
And you said earlier they have this weird confinement thing.
Yes, color confinement. It's a fundamental aspect of the strong force. You can never find a quark by itself. They're always bound together in groups that are color neutral. We call these composite particles hadrons.
Hadrons, okay. And what kinds are there?
Two main types. Mesons, which are made of one quark and one antiquark, and baryons, made of three quarks.
Like protons and neutrons.
Exactly. Protons, two ups and a down quark, and neutrons, one up and two down quarks, are the lightest and most stable baryons, forming the nuclei of atoms. Quarks also have electric charge and weak isospin, so they interact via electromagnetism and the weak force too.
So they feel three of the forces. Okay, what's the other family of fermions?
The leptons. Again, 6 flavors.
These are particles like the electron.
Yes, you have the electron, the muon, and the tau. These are the charged leptons, each with an electric charge of -1.
Muon and tau are like heavier electrons.
Basically, yes.
Yeah.
And then each charged lepton has a partner, a neutrino. So you have the electron neutrino, the muon neutrino, and the tau neutrino.
Ah, the neutrinos. The ghostly ones.
Very ghostly. They have 0 electric charge, and they don't carry color charge. So they don't feel the electromagnetic or the strong force at all.
They only interact via the weak force and gravity.
That's right, which is why they're incredibly difficult to detect. Trillions pass through you every second without you noticing.
Wow. And you mentioned generations before, for both quarks and leptons.
Yes, they naturally fall into 3 generations, or families. Each generation is like a heavier copy of the previous one.
So generation 1.
That's the up quark, the down quark, the electron, and the electron neutrino. These are the lightest and, crucially, the stable ones. All ordinary matter, everything around us is made just from these first-generation particles.
Why only the first generation for everyday matter?
Because the particles in the second generation, charm quark, strange quark, muon, muon neutrino, and third generation, top quark, bottom quark, tau, tau neutrino, are much heavier and unstable. They decay very, very quickly into first-generation particles.
So we only see them in high-energy places?
Exactly, like particle accelerators or cosmic ray impacts. The only exception is the neutrinos. Neutrinos from all 3 generations seem to be stable, and they constantly zip through the universe.
Okay, so that's the matter side. Quarks and leptons in 3 generations. Now, what about the forces, the bosons?
All right, the gauge bosons. These are the force carriers, the messengers. They mediate the interactions. There are 4 fundamental types we know of in the Standard Model, all with spin 1.
Let's start with the most familiar one, maybe, electromagnetism.
Okay. The force carrier for electromagnetism is the photon. It's massless, travels at the speed of light, and it interacts with anything that has electric charge.
Light itself is made of photons, right?
Yes, and virtual photons are exchanged whenever charged particles interact, like electrons repelling each other. This is all described by quantum electrodynamics, or QED.
Okay, next force, the strong one.
The strong force is mediated by gluons, G. They glue quarks together inside hadrons. Like sotons, they are massless.
But you said there are different types of gluons.
Yes, there are 8 distinct types of gluons. This relates to the different types of color-charged quarks can have. And unlike photons, which are electrically neutral,
Gluons carry color charge themselves.
they do, which means gluons can interact directly with other gluons. This self-interaction is part of what makes the strong force so complex and leads to things like confinement and asymptotic freedom. The theory describing this is quantum chromodynamics, QCD.
Fascinating. Okay, force number 3, the weak force.
Mediated by 3 particles, the W+, W, and Z bosons. Unlike photons and gluons, these guys are heavy, very heavy.
And that mass is important.
Crucial. It makes the weak force very short range. The W bosons, W+ and W, carry electric charge, +1 or -1. They're responsible for interactions where particle flavor changes.
Like a quark changing type, beta decay.
Exactly. A down quark turns into an up quark in beta decay, emitting a W boson. And remember that weird parity violation? The W bosons only interact with left-handed particles and right-handed antiparticles.
Still seems strange. What about the Z boson?
The Z boson is electrically neutral. It mediates weak interactions where the particle flavor doesn't change. It's kind of like a heavy version of the photon, but it also interacts with neutrinos, which photons don't.
And these 3, plus the photon, are sometimes grouped together.
Yes, they collectively mediate the electroweak interaction, which is the unified description of electromagnetism and the weak force at high energies.
Okay, 3 forces down. Photon, gluons, W, and Z. But we keep saying the SM covers 3 of 4 forces.
Right. The missing one is gravity. The standard model simply doesn't include it.
Is there a hypothetical force carrier for gravity?
There is the graviton,
No.
but it's purely theoretical at this point, never been observed. Trying to mesh general relativity, our theory of gravity, with quantum field theory is one of the biggest unsolved problems. Gravity is just too weak at the particle level to study easily.
So a massive gap still remains. Now there's one more particle we mentioned, the Higgs boson. Not really a force carrier in the same way?
Not exactly. The Higgs is different. It's a spin-zero particle, scalar boson, theorized back in '64 by Peter Higgs and others.
And its job is giving mass.
Its job is to explain why most other elementary particles have mass, especially why the W and Z bosons are so heavy, while the photon is massless. That was a major puzzle in the electroweak theory.
And it does this through the Higgs field.
Yes. The idea is that all of space is filled with an invisible Higgs field. Particles interact with this field as they move through it. The stronger the interaction, the more inertia or mass the particle acquires.
Like wading through treacle?
That's a common analogy, yeah. Particles that don't interact with the field, like photons, just zip through their massless. Particles that interact strongly, like the top quark or the WZ bosons, are very heavy.
And the Higgs boson particle itself?
The Higgs boson is an excitation, a ripple, in that Higgs field. Finding it in 2012 at the LHC was the final piece of the standard model puzzle predicted decades earlier.
So it gives mass to quarks, charged leptons, W and Z bosons.
Yes, through what's called the Higgs mechanism and Yukawa interactions. And because the Higgs boson itself interacts with the Higgs field, it also has mass, a hefty 125 GeV or so.
Okay, let's briefly touch on the deeper math. You said quantum field theory, Lagrangians. Sounds intimidating.
It is mathematically complex, yeah. But the core idea is that the standard model is built on principles of symmetry. Its dynamics are described by a mathematical function called a Lagrangian.
Like a master equation.
Sort of. You postulate certain symmetries, like the laws of physics being the same everywhere and at all times, plus specific gauge symmetries related to the forces, and these symmetries dictate the form of the Lagrangian.
And this equation has numbers in it.
It does. And this is a key point, maybe a slight weakness. The standard models doesn't predict the values of certain fundamental constants. There are 19 parameters in the basic model.
19. Like what?
Things like the masses of the quarks and leptons, the strength of the forces, coupling constants, and the mass of the Higgs boson itself. We have to measure these values experimentally and plug them into the equations.
So we know the rules of the game, but we don't know why the pieces have the specific weights they do.
That's a pretty good way to put it, yes. The theory works incredibly well once you plug in those 19 numbers, but it doesn't explain where those numbers come from.
And the Higgs mechanism is key to the mass part of that.
Yes. The Higgs field having a non-zero value everywhere, its vacuum expectation value, breaks the electroweak symmetry and gives mass to the W and Z bosons. The photon stays massless because of how the symmetry breaks. Then the interaction of the fermions with this Higgs field gives them mass too.
Wow. Okay. It's intricate, but it holds together. Let's quickly recap the forces themselves just to make sure we've got them straight.
Sure. So 3 forces in the SM: electromagnetism, weak nuclear, strong nuclear, all mediated by exchanging bosons.
Electromagnetism, carried by photons, acts on electric charge, long range, holds atoms together, chemistry, electricity. QED?
Perfect. Weak nuclear force, carried by massive W and Z bosons. Short range, responsible for certain particle decays like beta decay. Changes particle flavor, W bosons. Violates parity. Unified with EM as electroweak force.
Got it. And strong nuclear force, carried by gluons, acts on color charge, binds quarks into hadrons and holds nuclei together via the residual force, exhibits confinement and asymptotic freedom, QCD.
You've nailed it. That's the force landscape according to the standard model.
So this model has been incredibly successful. Predictions confirmed.
Time after time. W and Z bosons, gluons, top quark, charm quark. Their existence and properties were predicted before discovery, often with amazing accuracy. The Higgs was the final predicted piece found in 2012. Its predictive power is undeniable.
But there's always a but in science, isn't there? It's the theory of almost everything. Let's talk about the edges, the problems, the things it doesn't explain. Where does the standard model fall short?
Right, this is where things get really interesting for the future of physics. There are quite a few significant gaps and puzzles.
Like, what's the biggest one we keep mentioning?
Gravity. It's just not in the model. Our best theory of gravity, general relativity, is fundamentally incompatible with the quantum field theory framework of the standard model. Merging them is a huge theoretical challenge. No accepted theory of quantum gravity exists yet.
And the graviton particle remains hypothetical. Okay, what else?
Neutrino mass. The original Standard Model predicted neutrinos should be massless, but experiments starting around the late 90s definitively showed they do have a tiny mass and they oscillate, changing flavors as they travel.
So the model had to be patched.
Essentially, yes. We can accommodate neutrino mass, perhaps through interactions with the Higgs or other mechanisms like the seesaw mechanism, but it requires adding new parameters, potentially 7 or 8 more arbitrary constants to the model. It doesn't actually explain why they have mass or why it's so small.
So adding more numbers we just have to measure.
Exactly. Which ties into another criticism, its inelegance or perceived ad hoc nature. Those 19 parameters, or 26, 27 with neutrino masses. Why those specific values? The model doesn't say. They seem arbitrary, fine-tuned. Physicists often prefer theories where such values arise naturally from the structure.
It feels less like a fundamental explanation and more like a very accurate description that needs some numbers filled in.
That's a fair critique. This also connects to the hierarchy problem. The Higgs mass is sensitive to quantum corrections that theoretically should make it vastly heavier unless there's some incredible, unexplained fine-tuning cancellation happening. It seems unnatural.
Like the value is balanced on a pinhead?
Sort of, yes.
Yeah.
It suggests maybe there's new physics at higher energies that stabilizes it, like supersymmetry, but we haven't found that yet. There are also theoretical worries about quantum triviality, questioning if interacting scalar fields like the Higgs are mathematically consistent at all energy scales.
Okay, theoretical issues. What about cosmology? How does it fit with our picture of the whole universe?
That's another major area of tension. The Standard Model fundamentally clashes with observations explained by the lambda CDM model of cosmology.
How so?
Most dramatically, dark matter and dark energy. Observations tell us about 27% of the universe is dark matter and 68% is dark energy. That's 95% of the universe. The Standard Model contains no viable particle candidate for dark matter and offers no explanation for dark energy.
So it only describes the 5% we can see. Wow.
Pretty much, yes. It's a theory of ordinary matter and its interactions, but it seems ordinary matter is just a small fraction of what's out there.
Any other cosmological clashes?
Yes. The matter-antimatter asymmetry. The Big Bang should have created equal amounts of matter and antimatter, which would then annihilate each other, leaving only radiation. But we live in a universe dominated by matter. The Standard Model does have mechanisms for slight asymmetry, CP violation,
Yeah.
but not nearly enough to explain the observed dominance of matter.
So we shouldn't exist, according to the model.
Well, it struggles to explain why we exist in a matter-dominated universe, yes. Also, it doesn't naturally incorporate cosmic inflation, the idea of a rapid expansion phase in the very early universe, which is needed to explain why the universe looks so uniform and flat on large scales.
So fundamental inconsistencies with the universe we actually observe.
That's right. All these issues, gravity, neutrino mass, dark matter, dark energy, matter asymmetry, the hierarchy problem, the arbitrary constants, strongly suggest the Standard Model, despite its incredible success, is incomplete. It's a stepping stone, not the final theory.
The quest for a theory of everything continues.
Absolutely. Physicists are exploring many avenues beyond the Standard Model: string theory, supersymmetry, extra dimensions, modified gravity. But so far, no proposed extension or unified theory has gained wide acceptance or experimental verification.
So recapping this deep dive, the Standard Model is this phenomenal achievement, describing 3 forces and all known elementary particles with stunning accuracy.
Validated by decades of experiments, culminating in the Higgs discovery. It's built on the elegant framework of quantum field theory.
But it's clearly not the whole story. It leaves out gravity, can't explain neutrino masses naturally, has nothing to say about 95% of the universe's content, dark matter energy, struggles with matter-antimatter asymmetry, and relies on a set of seemingly arbitrary constants.
Precisely. It works incredibly well within its domain, but its limits clearly point towards deeper, undiscovered physics.
Which brings us to a final thought for you, our listener, to ponder. We've talked about those 19 or maybe even 27 seemingly arbitrary numbers, the fundamental constants plugged into the Standard Model from experiment. What if they aren't arbitrary? What if they are specific outcomes of some deeper, simpler, more elegant underlying principle of the universe that we just haven't discovered yet? What does it really mean for our understanding of reality if our theory of almost everything still relies on knowing the answers to these fundamental questions beforehand rather than predicting them from first principles?